In today's lesson, I want us to talk about the summary. We're just going to be focusing on the summary of continuity and limits. Of course, when we are talking about continuity, we cannot say we have completed the lessons on continuity if we haven't mentioned the intermediate value theorem and Bolzano's theorem. We usually leave sometimes we usually leave this behind because the proofs of these particular theorems are only suitable for students who are doing pure maths, and in this course you are not doing pure maths. We are actually looking for the maths that you need in order for you to prosper in your careers and also in your studies. We only focus here on the use. In most cases, the use that we focus on is how to apply these theorems. Sometimes we mention these theorems, sometimes we don't. For instance, when we're dealing with factorization, you'll find out actually there is a relationship between the methods of factorization and Bolzano's theorem, even though we did not formally state it, but we know that actually some of the information in this theorem was actually used when we're factorizing, and also Bolzano's theorems is actually the child of intermediate value theorem. That is why these ones is also worthy to mention them, even though we don't usually examine this directly in the course, but it's worthy to know that they actually exist. And also, when we're talking about limits, we cannot say we completed the lessons on limits without mentioning the precise definition of a limit. Of course, precise definition of a limit is only done by pure maths students who are actually doing pure maths, not in this course, because this course is so much intense with so many topics that you have to cover within a semester. So that is why some of the things we usually just mention them because we want to use them, but we don't usually prove much of these theorems. We can try if we know that at least you can grasp this content in a short period of time and mention that, okay, to prove this theorem you do 1 and 2 and 3, but in most cases we don't usually do that because in this particular course we don't focus more on the proofs. We want to how to use these particular theorems. Now let us start with continuity. We talked about continuity. I want us to remember some of the important points on continuity. When we're dealing with continuity, we said that a function, I'm going to call this function f, is said to be continuous, right? Continuous. This is n okay, let me write this normally. Is continuous. Yeah, it is said to be continuous at the real number x is equal to a if 3 conditions are met, right? The first condition that we said that if I take this this value x is equal to a and I plug it in this function f of x, so in the value of x I'm plugging in this a, I must get a value, right? In other words, f of a is a real number. It is a real number. In other words, f of a, I can also say that f of a is defined. So that's the condition number 1. This must be defined. Or another way to say this, we might say that a is contained. It must be contained in the domain of f. So if you know the domain of this function here and you know that a is contained inside, then condition number 1 is satisfied. So this one must be equal to some value, some real number, or this one must be defined, or this one must actually be this value a must be contained in the domain of f. And then we said that the second condition that we actually said, we said that the limit as x approaches a of f of x must exist. Right. So we said that this limit must actually exist. What do we mean by saying the limit must exist? We mean that the limit as x approaches a on the left of f of x, it must be equal to the limit as x approaches a on the right of f of x. That's what we mean by saying that this limit must exist. So the left and right must also be equal. And then the last one now here, which is the last condition, is saying that if I take the limit as x approaches a of f of x, this must be equal to that value that we get when we're plugging in a in this function. So we must actually get f of a. So if you look carefully in these three functions, they are saying that, and these three conditions, they are just saying that when I am drawing this function from the left of a to the right of a, I must draw this function without lifting my hand. So if I am lifting my hand, then that function, if let's say here I have this is my x is equal to a, and this is the output somewhere there. When I'm drawing the function from the left of a to the right of a, I must continue to draw the function without lifting my hand. Once I lift my hand somewhere here, then the function is not continuous at that particular point. That's the meaning of these three conditions. That's what we said. And please make sure that when this question is saying or asking you is f continuous at x is equal to a, that you look if this condition is satisfied, you look if this condition is satisfied, and you look if this condition is satisfied. That's what we actually said. And we said that if let's say I have a function here, and my function is something like this, and there is a hole somewhere, and we're going like this one here, even if there is a dot somewhere that is shaded somewhere there, as long as there is a hole somewhere there, this one, we said that at this particular point here a, the function is not continuous because I cannot continue to draw because there's nothing there. So we called this point that at this point f is not continuous at that point, and the name of that discontinuity is removable discontinuity. So this one, we said it is a removable discontinuity. That's what we said. And if let's say now we have our f of x, and around point a we actually having something like this, the function is going this way, and also this side is going that way, or the function is going down this side is going that side, or it's going this side and this one is going downwards like this, or this one is going downwards and this one is going up, or this one is going up, this one is going down. At this point we can see that this function is actually not continuous, and because at this point we have a vertical asymptote, we called this infinite discontinuity. So whenever you have a vertical asymptote there, that's an infinite discontinuity. We don't say negative infinite, it's just infinite discontinuity. Even if they are both pointing this side, it's just infinite discontinuity. There, the function is not continuous, infinite discontinuity. And then we talked about the third one, and the third one we said that whenever I have a function that you can draw like this, and then after some point I start drawing the other piece something like this, even if there is a hole here and also there is a hole there, as long as to move from here to there I have to actually jump, you can see that at this particular point here there is actually a jump discontinuity. So this one we usually call a jump as just jumping, because you jump to move there, so it's a jump discontinuity. So that's what is actually happening here. So it is a jump discontinuity. Another thing that we can actually look at here, if let's say now I shade this, that one is not shaded, it's still a jump because this function is not continuous. The limit on the left and the limit on the right, they are not the same, so it's not continuous. So this one, we called it a jump. You jump, or just someone might say that to move from here to there, I have to step up. So this is a jump discontinuity. So we talked about these three discontinuities. These are some of the things that you need to know around discontinuity at a particular point. Then we started to talk about continuity. Continuity on an interval. On an interval. If let's say we have an interval, I have an A here and I have a B. Take note that these two are closed. So because of this here, what we need to find out is that we want this condition. The condition is still the same. It's just that now, because here this is an interval. So if this interval here, I'm just gonna give you a quick summary of this whole thing. If this interval here is actually the domain, is actually contained inside the domain of f. Let me write this here. We have this interval here. This interval a b is contained in the domain of the function f. Then we say that this function is continuous on this particular interval. But now you can say that actually, if you know that a and b, these values are actually part of the domain or are inside the domain of this, you can conclude that f actually is continuous on this particular interval. But most examiners, when they are actually asking you, is f continuous in this particular interval, what they want you to find out is find the limit as x approaches a, but now a, we're gonna approach it on the right, of f of x, and they want this limit to prove, is it actually equal to f of a. If it is equal to f of a, then condition number one would be satisfied. And then secondly, they want you to find out the limit as x approaches a. Now we're going to b, as x approaches b, but b now on the left of f of x. Is this actually equal to f of b? That's a question mark. So if this one is satisfied, then the last condition that they want you to do, they want you to pick some value inside this domain, inside this interval here. So the limit as x approaches some c of f of x, is this the same as f of c, where c now is an element of a and b. In other words, here c is a value that is in between. So if I pick a value in between here and I plug it in this function, am I gonna get f of c? That's what most examiners are looking for. But looking into this whole thing here, by just noticing that actually this interval here is contained in the interval of in the domain of f of x, you are automatically proving that these conditions are actually satisfied. So that's what is actually about continuity on the interval. Now, after doing that, we actually talked about the theorem, and we said actually theorem is not like this. We talked about a theorem, and we said that if I have two functions, I'm going to say if f and g are functions, and these functions are continuous, they are both continuous at x is equal to a, and and we have, and c is a a constant. C is actually a constant. Then the following functions, let me just say the following functions here. The following functions are also continuous at x is equal to a. Of course, we're not going to prove this, but proving these things is actually straightforward. You can actually take it as a homework and prove it and see if you can. So I have these functions. So I have 1, 2, 4, 5 functions are also continuous at a. What is the first function? So if I take f of x and I add g of x, this function also is continuous, because if I take this the limit of this, because it's continuous, it's going to be f of a, and the limit of that is also going to be f of a. Therefore, this has also have to be continuous. Let me say for this particular question, I can say I'm going to prove it. I'm just going to prove one just to see how this thing is actually working. And then if I take f of x and I subtract g of x, this is also continuous if these two are continuous. And if I take a constant times f of x, this one is also going to be continuous. And if I am taking f of x times g of x, this is also continuous. And if I am taking f of x divided by g of x, given that g of a is actually not equal to 0, then this function is also continuous. Those are actually other functions that follow from knowing that this function and that function is actually continuous. An example of this will be if I know that f of x, you know that f of x is equal to x squared. I know that this function is actually continuous, right? And now I have my g of x. G of x, I'm going to say it is 2x. And I know that this one is actually a linear function, a straight function, so it is continuous everywhere. Because I know that this function is continuous and that one is continuous, then my h of x, which is equal to x squared plus 2x, this I know is continuous, this one I know is continuous, then this addition of these two must be continuous. And even if I were to change now and put a minus, because this one and that one is continuous, then this has to be continuous also. And also if I were to change this whole thing now, this is continuous everywhere and this one is continuous everywhere, then adding is going to be continuous everywhere. And even if I multiply this, I know that this one is going to be continuous everywhere. But now, if I am looking some h of x, which is equal to x squared divided by 2x, because this one at x is equal to 0, x is equal to 0 is not part of the domain of this whole function. Or this one at x is equal to 0 is going to be 0, which is actually violating this part here. So we can say that this one is continuous everywhere, except when x is equal to 0, because when x is equal to 0 is not part of the domain of this. And also secondly, not only that, we know that the limit as x approaches 0 on the left and on the right is actually not the same as the value, because the value is undefined, but the limits at those particular point is actually going to be a 0, right? So that's also another way to look into it. This is not part of the domain of this, therefore it is not continuous at that point. So let me try and see if I can give you an overview of this. Suppose that I'm saying, suppose the functions f and g are continuous at x is equal to I'm just gonna say at x is equal to a here. Prove or disprove that f plus g, no, plus g is continuous. So how do we end up proving this whole thing? Solution. I'm just trying to illustrate how someone can actually go about proving this 1, 2, 3, 4, 5 statements. So let us look into this. Let's start by saying f is continuous. I'm gonna say here f is continuous, right? So I'm gonna look into that. Suppose these functions are continuous at x is equal to, prove or disprove that this one is continuous also. So if f is continuous, what this simply means, it means that f of a, if I were to take this value a and plug it in f of x, I am going to get some output L. And then secondly, if I were to take the limit, there were three conditions here. The limit as x approaches a on the left of f of x, it must be equal to the limit as x approaches a on the right of f of x. And lastly, the last one is saying that the limit as x approaches a, because these are equal, they have to be equal to this, of f of x must also be equal to L, which is the same as f of a. So these are the conditions that come from knowing that f is continuous. If f is continuous, these conditions are happening. If these conditions are happening, then f is continuous. So we have this vice versa. And then secondly, we know that g is continuous. Because g is continuous, these three things need to happen. That g of a must be equal to some value, I'm going to call it m. And if I take the limit as x approaches a on the left of g of x, it must be equal to the limit as x approaches a on the right of g of x. The third condition is saying that the limit as x approaches a of g of x must be equal to the value of this function, which is m, g of a. Now, we have these three conditions here. Now, how do we prove now? Now, the questions that we have, we wanted to prove that if I take f of a, right, plus, remember that I want to prove that if I take f plus g of a, I actually get f of a plus g of a. Let me look into this again. The first condition is saying we must actually have the same value, and that's what we want to prove. And then secondly, we want to prove that the limit as x approaches a of f of x plus g of x, which is the same as this whole thing is the same as actually. So when I'm writing f plus g of x, this is just the same as f of x plus g of x. So this is just the same thing. So if I have this limit as x approaches a, this, I want this to be the same as f of a plus g of a. That's what I wanted to prove. So this is the question mark. I already know that this is happening. Now, how do I prove this statement here, that these two statements that are actually true? So we know that if, let's say, I'm going to use a blue here. We know that if I were to say that I am actually looking for, let me start with f plus g of x. This one is the same as f of x plus g of x. That's the first thing that comes into mind. And then the second thing is, if I look into f of plus g of a now, in the value of x I'm plugging in a, I am actually getting f of a plus g of a, and I know that my f of a, we called it to be L. looking into this equation here, we said it was L. And if you look into actually g of x, right? G of x, when I'm plugging in a, we said that this is actually m. And if you look carefully into this L here, we said that L is actually the same because this f of a is L, and L is the same as the limit as x approaches a of f of x. So this part here is the same as the limit as x approaches a of f of x. And if you look into this part, it was the same as the limit as x approaches a of g of x. And looking into this part here, you can actually see that technically speaking, this limit, we know that it exists, and this limit here, we know that it exists, which means that using the rules of limits or the rules for limits, this is actually the same, because this limit here is the limit as x approaches a. We have x approaches a, we have x approaches a. This exists, therefore this must be the same as the limit as x approaches a of f of x plus g of x, right? And if you look carefully into this part here, this is just the same as the limit as x approaches a of f plus g of x. And now, because of that, you can see that I have found out that if I were to plug in a in this function here, I am actually getting it to be equal to the limit. And actually, that's why we have actually proved this this theorem here, but for condition number 1. You do the same thing for 2 all the way up to 5. So that's how we prove this. But what is important is that whenever you know that there are two functions f and g and they are continuous, then their addition must also be continuous, their subtraction must be continuous. Multiplying by a constant, we get a continuous function. Multiplying those two functions, the product of two continuous functions is also continuous, and also the quotient of two continuous function is continuous as long as the function in the denominator is not equal to 0 at that particular point. So that is what is actually important. Now, speaking of which, we also said something that is actually important here, where we said that a function is continuous in every point in its domain. So we said that because of that, the following functions are also continuous in their domain. The following types of functions are continuous at every real number in their domains. They are continuous in every number in their domains. So if, let's say, you are talking about polynomials or polynomial functions, they are continuous in their domain. And then if you are talking about power functions are continuous in their domain. And if you are talking about exponential functions are continuous in their domain. And if we are talking about rational functions they are continuous in their domain. And then if you talk about trigonometric functions, they are also continuous in their domain. And if we are talking about logarithmic functions, they are also continuous in their domain. So we know these functions. The main idea here is that it is always nice to work with continuous functions. That's why it is good to mention them, that these functions are continuous in their domains. Now, let us take a quick recap on something that we did before. We said that if, let's say, I have a function f and I'm not just gonna write f. Let me just put f of x here so that you know. And I have f of x and I have g of x are functions, right? They are functions. Then the function that is written by f, we have this little circle in between of g of x. We said that this function here is actually the same as f of g of x. The meaning of this whole thing is saying that you have a domain of g of x and you pick an x in that particular domain. So this is the domain. I pick x that is inside, and then I plug this one in g, and then I get a value in the range of g. So I get a value in the range of g. This is actually g of x, which is in the range of g of x. Then take that value and take it as a domain of this value here. It must be in the domain of f, and I take that value and I plug it in f. Then this whole thing here, which is that, is actually the final output. Is actually the final output, which is f of g of x. Other people, in order for them to actually realize, they can say that I take x, I plug it in g, and then after g, I'm gonna get some g of x, which is equal to some value b, and this value b is in the range of f, in the range of g, I mean. And then I take this b, I plug it in f, and then I get my f of b. So whereby this b is the output of this function. So the meaning of this whole thing is actually saying that I have a series of functions that are being plugged. I'm plugging inside another function. I'm plugging inside another function. Just to also mention another good example, if someone were to say that I have my h of f of g of x, right? So I take my x in the domain of g, and then I'm gonna plug it in g. I get my g of x, and then after getting that value, I am plugging it in f to get f of g of x, f of g of x. And then after getting that output, I'm plugging it inside h. I get my h of f of g of x. This is just the series of getting or a value. I plug it inside another function, and then from another function I actually say that I have another nice function. So I take this and I plug it inside, I get an output, and another example will be, I actually have looking into this, I am going to have of this, and then I have that. So let's say now I had an example of f of x was equal to x squared, and then g of x was actually equal to 2x, and then I have h of x. H of x is also equal to the root of x, right? So basically here, if I want, let's say I'm looking for actually h of f of g of x, what is that going to be? I don't know what this is actually is, but what I know is that first I want to take my x, and then I take my x and I plug it in g to get g of x. What is my g of x? G of x is just equal to 2x, and then I'm taking this 2x and I am plugging this 2x in inside this f here. So I'm gonna have an f here. So I am supposed to get f of g of x. Take note of this, that instead of having f of x, instead of x I have g of x. So in the value of x I am going to plug in g of x. So this whole thing here is going to be actually going to be f of g of x is the same as 2x, and now I'm gonna take this and plug it in f of x. So what was our f of x? F of x actually was x squared. So we had something squared. I had x squared. So I had x squared. So in the value of x, we don't have x here, we have 2x. So in this particular value here, I am actually going to have 2x, which means that this whole thing is going to be 2 squared is going to be 4x squared. So we end up having that. And now I take this f of x and then I plug it in h of x. So in the value of this, I'm supposed to get h of f of g of x. You get what I mean? And now, looking at this particular thing that is inside, I am taking this whole thing and I'm plugging it in the value of x. So this one here is actually h of 4x squared. What was actually h of x? H of x is actually the square root of something, but that something here is what is sitting in the value of x. So we get 4x squared. So if you look into that, of course we know that this actually is the same as just the square root of 4 times the square root of x squared, and the square root is always going to be positive, so we'll end up having a 2, and the square root of this the square root of x squared is the same as the absolute value of x. So this is actually the final answer. So if, let's say, now we're looking for this, this is symbol, I'm gonna take this and I'm gonna plug it inside here to get 4x squared, and then what we just did here, it was just this one, it was just, we had h of f of, what was g of x, 2x, and then at the same time it's going to be h. So I'm going to take this and plug it inside. So we ended up having 4x squared, and then this whole thing now ended up being 2 absolute value of x. So that's how this whole thing became. Even if, let's say, you decide to stop at 2 times square root of x squared, it's still fine. There's nothing wrong, because this is just the same as the absolute value of x, this and that. So there's nothing wrong. So now that we have talked about this nice thing here, I want us to introduce another theorem on actually continuity. So this theorem is just saying that whenever you have, suppose that if f is a continuous function, or let me say f is continuous, let me just say it is continuous. F is continuous at b, right? So it is continuous at b, right? And we know that the limit as x approaches a of g of x, what is actually happening here, so of g of x. So I have two functions here, f of x, and f of x is continuous at this point, and the limit as x approaches a of g of x is equal to b, right? Then the limit as x approaches a of f of g of x is just equal to f of b. This actually makes a lot of sense, knowing that as this function here, as x approaches a, we know that as x approaches a, this function that is inside here is actually approaching b. And we know that f is continuous at that particular point here. Because f is continuous at that particular point, we can actually get the limit of this whole thing to be equal to that particular point. And another way to look into this here, the output output of this inside function becomes the input of that function. So to find the limit as x approaches a of this whole thing, we just want to find what is actually the value that this function, this part is actually approaching. And of course, we'll actually get to a nice position here. If you go back to the rules for limits, we said that if I know this, let's look, if this function I know that it is continuous, one thing for sure is this: the limit, I want you to just grasp this thing here, of f of g of x. This limit here is just the same as f of the limit as x approaches a of g of x. And we already know that this thing that is inside here, it was just a b. That's how we ended up having this this nice thing here. So just know that whenever this is continuous at b, and I know that the limit as x approaches a of this is b, then the limit of the composite function must actually be the output of that, because this one is continuous. If it is continuous at b, I can plug in b. That's how this thing comes from. And another nice theorem here is saying this. These theorems, once you grasp them and then you put them in your head, it's easy to use them. If g is continuous, so we have g is continuous at x is equal to a, and f is continuous, at g of a, then looking into this, because this one is continuous and f is continuous at this output here, which means now I want to take this and plug it inside there, then the composite function, so if I look at the composite function f of g of x given by the composite of f and g of x, which is just equal to f of g of x, is also continuous at x is equal to a. So basically what is important here, I want you to keep track of this. Here I want this function, the outside function, to be continuous at that point. And secondly, the limit of the inside function, I want it to exist to be equal to some value. If the limit is equal to some value, then I know that to find the limit of this function as x approaches a, I just need to find the limit of the inside function, get the value and plug it inside, because that one is already continuous. And then this one is saying both these two functions are continuous at x. This one is continuous at x is equal to a g, and because this one is an inside function inside f of x, then the output of that function at this particular point must also be a point whereby f is continuous. If that is the case, then the composite of these two must also be a continuous function. That's what is actually important about this particular function. So this is just a little bit of summary and adding up of some of the information that is actually needed in this particular case. And now, because we have that, I want us to talk about the intermediate value theorem now. So the intermediate value theorem, or others they just say is IVT, intermediate value theorem. What is it saying? If a function If a function f is continuous on a closed interval, so I have a closed interval a and b. Take a note that these are the x values. So we have x, these are the x values. It's not x and y like coordinate. These are the x values, right? Suppose f is continuous and n is any real number. It is any real number. So we have n is any real number between f of a. So I take the output, I take a and I plug it there, I get this output. So it is between f of a and f of b. So I will find the output of these endpoints there. Then there exists at least one real number c. This c here is in between a and b. So there exists an irreal number that is between a and b, such that when I am taking f and I'm plugging this value c here, I get the n, which is that with this n here. Let me try and explain here. I'm gonna use a blue to illustrate here. Suppose I have a function here, and this function of mine is continuous. In other words, is continuous between this value a and this value b. So x is equal to a and b. This function is continuous, which means I can start somewhere there and I draw this point here is defined, and at this point I have f of a, and I can start from this point and draw this whole function all the way up or down, and this one here I know that its output is going to be f of b. What this theorem is saying is this: whenever I pick a point here whereby this point is n, is in between this point here, let me use a red. I have a point here, I pick a point there, this point is n. This theorem is saying that there exists a value that is in between. So there exists a value here, this value is c, it is between a and b, such that if this function here is f, when I'm taking f and I'm plugging in this value c here, I get n as the output. That's what this is saying. It's not saying that there is only one value. It's saying that there exists one, which means it can be 1, there can be 2, there can be 3, but this theorem is guaranteeing that once you pick a value that is in between this point and that point there is always gonna be that point here is an image of an x value that is in between these 2 points. I did not talk about anything that has to do with an increasing function. Let's say I have a point here and this is my a, and this one here and this point here is my f of a, and this point is increasing and then it comes down, it increases and then it comes down here, and this point here is going to be my b. So what this thing is saying here, if you look here at this particular point here, this is the output f of b. If I were to pick a point that is in between these points, so I pick a point here, I'm going to make it a blue. I pick a point here, and this point I call it n, and I go to the function there. This theorem is saying that there exists an x value that is in between these 2 points, and that point is c, such that if I take f of x and I plug in that value, I'm going to get an n. It doesn't mean that pick any value in the function. It's saying that pick a point that is between this output and that output. So once I pick a point here, I am no longer obeying the theorem. I need to pick a point that is in between these two bounds. So this function, I can only hit it here. So that is what this theorem is actually saying. Let's take an example here, a realistic example. I'm going to make it black. This example here, I'm going to call it an example, or example 1. Suppose f of x is equal to x cubed, right? And we wanted to consider the closed interval. So this closed interval is 1, 2. Now, the question will be like this. If you were to pick a point, an output that is between the output of this and the output of that, are we going to get a point that is an x value that is in between this as the input? Let me repeat what I'm saying here. If I were to look here, f of 1, and look here, f of 2, right? I take the value that is in between these 2 points. Can I get an x value that is in between these 2 points? That's actually the question, that that's how the question will actually go in this particular question. So now what we're actually going to do here, we first you just have to look at f of 1. If I will take this 1 and I plug it here, I will get 1 cube, and 1 cube is 1, and I get f of 2. And then if I look at f of 2 and I cube it, I will get 2 times 2 is 4, times 2 is going to be an 8. Now I have 2 outputs. Now what you do actually, we pick any number. I'm just gonna pick any number n between 1 and 8, right? We're gonna say this number is this. If I were to pick 9 is bigger than 8, it's not less than 1, and it's also not it's not bigger than 1. It's not bigger than 1 and less than 8, right? So basically we want to pick a y value that is less than let me move this, less than 8, and this number must be between 1, which is this one. So now, can we get an x value that is less than 2 and also bigger than 1? This one here is this one, and then this 2 is this 2, and this y here is the value that we are picking, right? So we want to see if its input would be always in between that. So let's say now I'm gonna pick a value. Let's say I'm gonna pick my y to be equal to a 5. So my y is equal to a 5, or my f of x is equal to a 5, right? So how do we proceed? What you say here is that since f of x is, take note that the domain of this function here, the domain of this function is just x is an element of real numbers, or you can say that negative infinity is less than x and x is less than positive infinity. So this is the domain, or you can write it this way. Now, if you look at this interval here, this interval here is contained inside this interval here. Therefore, f is continuous on the interval 1, 2, right? So on the interval x, where x is in between this, so x is actually, f is continuous. Since f is continuous in this interval, right, then the intermediate value theorem guarantees us that there exists at least one real number. There exists at least one real number C such that if I take this and I plug it inside C, I actually get a 5. Right. What this simply means, it means that if I would take C cube, I would get a 5, which actually implies that C must be equal to the cube root of 5. And now if you look into this value here, if let's say I'm going to look into that value here and say that I want this a 5 here, that value is approximately equal to 1.71, right? And this value here, you can see that this value is actually bigger than 1. So this value is actually bigger than, I can just do this, 1. And then this value is less than 2, which means actually this value here is actually obeying what this theorem is saying. That's what this thing is usually saying. So what is the use of this thing? Sometimes you cannot find that value, but because of knowing the intermediate value theorem, you know that it is there. That's what is important here. It means that I have this. You just want the output of these two functions. Pick a value that is in between these and then actually solve for x. And that x actually will always be in between these two values as long as the given function is actually continuous. Let's go to Bolzano's theorem. Bolzano's theorem is actually the application of the intermediate value theorem. Bolzano's theorem. What Bolzano's theorem is saying is this: if a function, I have a function here, f, and this function f is continuous here. It is continuous on a closed interval. So this function is continuous on a closed interval, and I'm going to call this interval AB. And when I'm actually taking the output of this, which is f of a, and I multiply with the output of that, which is f of b, I get the negative answer, or a value that is less than a 0. Then Bolzano's theory is saying that this is what is going to happen. There exist, this is, if this is happening, then there exists at least one real number C, right, where this C is in between A and B, right? So this one is saying that there must be a value in between A and B. It's not A, it's not B, it is a value in between, such that if I take this value and I plug it inside f, I get a 0. So Bolzano's theorem is saying this: if this value here, if I take this value and I plug it in f of x, I get a positive value, and when I'm plugging this there, I get a negative value. Or I plug in this one here, I get a negative value, and this one, when I'm plugging it there, I get a positive value. And I know that this function is continuous, then this function must actually have a roots. In other words, it must cut the x-axis. That's what this theorem is saying. If at least in this interval, one of these, the output of these two is negative and the other is positive, then this function must have a root, or it must have an x value whereby the output is 0. Or this function, if you were to draw it, it must cut the x-axis at some point, and that point must be C. It can either be 1, 2, or 3 points, but it exists as long as the output of these is one is negative and one is positive, right? Thus, this is actually the application. And if you noticed, when it comes to this, we actually, when we're dealing with the factorization using inspection and long division, you will find out that Bolzano's theorem is actually kind of the main reason why that is always true, that we look at the factors of the last term and then we plug them in. Once we get a 0, we know that it must be one of the factors. You can see that this one is kind of contained inside like that. Let's take some examples here. Maybe you will see it. And this one here will actually make a lot more sense when we are taking examples. I'm going to take, let me try and take 3 examples instead, not 1. This is going to be the first example. The first example is saying something like this. I'm going to say this is the first example. Suppose that we have, I'm just going to say, suppose that I have f of x, and f of x is equal to x squared minus a 4. And let me write here, suppose f of x is equal to this, and we consider the closed interval. So I'm going to consider the closed interval. I'm going to say I have 1 and 3 here. I have a closed interval. Now, if you look into this particular function here, the first thing that you need to do here is very simple. I'm going to take this and plug it in that function. So I'm going to end up having f of 1. And then if I'm plugging f of 1 here, I will end up getting 1 squared minus 4, which is 1 minus 4, which is equal to minus a 3. And if I'm plugging here f of 3, and I'm plugging this function here, plugging in this function, I will get 3 squared minus 4, which is the same as 9 minus 4, which is a 5. You can see that this one here is less than 0 or negative, right? And this one here is greater than 0 or positive. So what is important here is that one of these 2 outputs must be positive and one must be negative. It doesn't matter. This can be negative and that one is positive. At least one must be positive and one must be negative. And if I take f of 1 multiply by f of 3, I am going to get what? Minus 3 times times positive 5. This is going to be minus 15, which is less than 0. Now, the first condition of Bolzano's theorem is this one here, and it is satisfied, right? So this one actually is satisfied. The second condition that I want you to take note of is this. If I look at f of x is equal to x squared minus 4, the domain of this function is actually saying x is an element of real numbers, because here I can plug in any value. I can plug in negative values, this will be defined, 0, this will be defined, positive values, this will be defined. So the domain of this function is that. And now, when I'm actually looking at this interval that is given here, 1 to 3, so looking at this one here, I have 1 to 3. This one here is actually contained inside. So this interval is contained inside this this domain here. This one is contained because 1 is also a real number. Any number between 1 and 2 is contained. 1 and 3 is contained inside, and 3 is also contained inside. Therefore, we can say that f is continuous on the interval 1, 3. So f, we know that f is continuous on this interval. So the first condition is that when I'm multiplying these two, I get a negative value. This one was supposed to be minus 50, not minus 5. I get a negative value, which is point number 1. Second one, f is actually continuous. Therefore, you can say, therefore, by the Bolzano's theorem. There exists a real number C that is actually in between 1 and 3 such that f of c is equal to 0. So basically here what is important is not let me first talk about these brackets here. The reason I'm not using square brackets, you might be wondering why I've been using these instead of the square brackets, which is the given interval, and also when we're dealing with this I was using these open brackets. It's because of one thing. We already know the output and we are looking for the value that is in between. We don't want this value and that value. We want the value that is in between. That is why we are using open brackets instead of square brackets throughout. Repeating, I don't want this C to be this endpoints. I want a value that is in between. That is why I have been using the open brackets. So we might not know what is the value of C, but now that we know that it is within this interval, we can even use a computer to find that value C. Of course, in this particular example here, we know that if I were to plug in, I know that f of c, I'm going to plug in the value of x, c, I will get c squared minus a 4, and I want this to be equal to 0, which actually means that c minus 4 is the same as c minus 2, and c plus a 2 is equal to 0. In other words, c is equal to plus or minus a 2. Now, if you look at c is equal to minus 2, you can see that when I'm plugging in here c is equal to minus 2, I'm going to get a 0. But this value here is not inside here because minus 2 is less than minus 1, so it's not contained inside here. So let me say this one is not the one. But if you are looking at c is equal to a 2, you can see that 2 is bigger than 1 and also is less than 3. Therefore, 2 is within this interval, which is not bad because this theorem here is not saying that there is only one. It's actually saying that one of these roots must be inside here, which means I have this root and it is inside there. That's what is important. That's what Bolzano's theorem is saying, that within this interval, one of the roots of f is there, is within inside. If I know that f is continuous, and when I'm multiplying the output of the endpoints of the interval, I get a value less than 0, then one of these roots must be contained inside. And now let's look at example number 2. I'm going to take some example number 2. I'm going to take this very same example, but I'm going to change the sign. I'm going to say, suppose I have my f of x, and my f of x is equal to x squared plus a 4. And suppose that I consider, we consider f of x is equal to this. On the interval, I'm going to have here minus 2 and 2. Right. Now, I wanted to know if is one of the roots of this function contained inside there. So the question would be, is one of the roots contained inside there, or is there any value c such that f of c is equal to a 0? Is there such a value c which is contained inside there? So the first thing that we do, actually, we take this value here and we plug it in f. So I want to plug in minus 2, and I have minus 2, and I square it up, I plus a 4, and then minus 2 squared is going to be 4, 4 plus 4 is going to be 8. And this one is greater than 0, and if I take f of 2, I'm taking that value now, and I'm plugging it inside, and I'm going to get 2 squared plus a 4. And if you look into this, actually, we are actually end up with 4 plus 4, which is also 8 greater than a 0. Now, looking into this here, I have f of this value here is actually bigger than 0 and f of this value. Both of these are positive. Because both of the outputs of these values are positive, we cannot apply Bolzano's theorem in this case. We cannot apply Bolzano's theorem in this particular case. In matter of fact, because of this and that, we cannot apply. We cannot also say that because this is positive, the output of this is positive and output of this is positive, then there is no root inside. No, we cannot say that. All we can say is that we cannot apply Bolzano's theorem. We only apply Bolzano's theorem if one of the outputs of the endpoints is negative and the other is positive. That's when we can actually apply Bolzano's theorem. It does not mean that there is no root inside. We just cannot apply Bolzano's theorem. But in this particular case, you will find out that since x squared, if I plug a negative value and square it up, I will get a positive value. And if I'm plugging in a positive value and square it up, I will get a positive value. If I plug in a 0, I will get a 0. So since this part is always bigger than 0, and this actually means that x squared plus a positive value is always going to be bigger than 0. So in this particular case here, we can say that because for all the values that are actually inside here, we always get a value that is bigger than a 0. Therefore, f does not have a root. Or you can say that it only have imaginary roots because this is always bigger than 0. Whatever the root you're getting is just in your head. You're imagining it. So you have imaginary roots. So in this particular case here, someone might say that actually, looking into this function is continuous everywhere, and we know that it's always bigger than 0. Using Bolzano's theorem, then we can say that actually because these are always positive, then we can assume that this one is always, it doesn't have a root, or there is no such value c that can actually do that. But if you are considering just looking at the endpoints, because this is positive and that is positive, you cannot use Bolzano's theorem. But using this fact that this is always positive, this one is always positive or greater than 0, is positive or equal to 0, adding a 4 is always going to be positive, you can conclude that f does not have any roots. Let's take another example here and go to something that is so much important, which is the summary of limits. Let's look now at as actually the example 3 here. Hopefully you understood this, that the sign must change, because the sign did not change here, therefore we cannot apply Bolzano's theorem. But because we know that this happened, we can say that does not have a root. Now I want us, suppose the question is saying here, the thing is this here. Suppose we have a multiple choice question, or we are actually tasked with the actually finding the roots of f of x is equal to x cubed plus 6x squared, and then plus this is not plus, let's use minus 5x, and then we plus a 10. Right, so we have this function here. I want to consider this. Now the question that we actually have here, we want to find the roots of this equation here. Find the roots of this equation, of this function. or find the solution of this when we are setting it equal to 0, or we can say we want the zeros of this particular function. Now, the first thing that we said you must do when you actually want to find the roots of this, remember that we wanted to find the main goal here is to want to find x squared plus 6x x cubed plus 6x squared minus 5x plus a 10. We want this to be equal to a 0. So the first thing that we wanted to do here, we wanted to find the factors of this whole thing here, which is 10. So the factors of this, we have many of them. We can either have plus or minus 1. The second one can be plus or minus 2, because 10 goes 2 goes to 10 several times, and it doesn't leave a remainder. And when we go to 3, 3, 6, 9, so 3 does not go to 10 and not leave a remainder. It leaves a remainder, so we don't have a 3. And if we go to 4, 4, 8, so we don't have 4 is not one of the factors of 10. And then we go to 5, 5, 10, so 5 plus or minus 5 is one of the factors of 10. And then also here we also have plus or minus 10, because 6 does not go and 7 does not go and 8 does not go and not leave a remainder. Now, if you look at these factors of this of 10, you will find out that if I place these factors in a number line, this is what I want us to do here. These factors I have 1, 2, 4, 6, 8. So I have 1, 2, 3, 4, 5, 6, 7, 8. So here I am going to have minus 10, and here I'm going to have a 10. I'm going to have a minus 5 here, and then I'm going to have a 5 here. Here I'm going to have a minus 2. Here I'm going to have a 2, and here I'm going to have a minus 1. Here I'm going to have a 1. Now, I wanted to look at the outputs of these factors. If I am plugging in a 10 in this equation here, we can see that you can either plug it here in the calculator, or you can just try and work them out. And I can guarantee you that you will end up getting 1560 or 1560, or you can get 260 here if you're plugging in a 5. Here you're supposed to get a 32. Here you're supposed to get a 12, and here you're supposed to get a 20, and then here you're supposed to get a 36, and here you will end up getting a 60, and here you will get a minus 340. Now, you will notice that all these functions, ever since we started talking about the intermediate value theorem, we did not draw them. We only tried to actually find the positive where the function is positive and where it is actually negative. So if you look at this interval here between 5 and 10, this one is positive and that one is actually positive. So we don't usually consider this part here, and we move here. Between this one and this one, we still have a positive. So we have a positive here, you have a positive here, you have a positive in between, you have a positive here, you have a positive here, you have a positive there, and you also here have here you have a positive. But here, if you start looking into this value here, I get a negative, and here I get a positive. So this value C here, which is actually going to make this equal to 0, is actually in between minus 10 and minus 5. So whatever that value is going to be, what is important here is actually that whatever that value is going to be in between these two. So if you are using a computer and approximation, your starting points will be these points here. So that's what I want you to know. If you can't get the factors, but you can see that one or two of the factors, one actually have an output that is negative and the other is positive, which means actually the value C that you are looking for must be in between these two numbers. I mean, we are actually minimizing this. Why is it important to minimize this to this interval? Because if you're giving a computer to solve this problem, it will find that value here. But now, because the program will take a lot of time to actually end up finding out what is that value, is going to waste your time. But if you just first look at these factors and then you minimize, or you actually truncate the interval to be this small, at least the computer is going to take smaller time to actually find that value between these 2 points. That's what all about Bolzano's theorem and also intermediate value theorem. That's what is actually important and what you actually need to know about this. Now, considering the continuity of functions, I think that's all that you need to know. Now I'm just gonna give you a summary of how you actually solve limits using different methods that we actually have studied so far, because this is way more important than anything that we actually have done, because we have studied so much, and now it is actually important to know that at least solving limits, so that at least you know that if, let's say, I give you a limit, you know how to solve it. Continuity, you have some little bit background on top of that. And of course, there are some things that if you don't understand, it's always good to consult. Consultation is not like the lecturer is doing you a favor. Is actually you are paying to actually go to the class and also go to the consultation. So those consultation are within your rights. So it's always good to consult, and also it's always good for you to practice so that you can get it even more. Now, suppose the question is saying evaluate, or what is the value, evaluate, or what is the value of the limit as x approaches a of f of x. How do you solve a limit of this particular nature? How do you solve that? So basically, okay, let me first emphasize this. This value here, I want it to be finite, right? 5, 10, 15. I don't want a is not plus or minus infinity. So this is just a finite value. A is not that. How do you solve limits of that particular nature? If this value here, let me just do this here. I'm going to place a red. If a is contained, right, inside the domain of f. So a is contained inside the domain of f. So x is equal to a is part of the domain of f. What I actually mean by this, I mean that f is continuous, right, at x is equal to a, right? So f is continuous at x is equal to a. Then the limit as x approaches a of f of x is just gonna be the same as you take this value, plug it in, and then you get your f of a. That is supposed to be your limit. That is why I always say the first thing that you do, take x is equal to a and plug it inside f of x and see what you are getting. This is where this whole thing comes from, is that if f is continuous at this particular point, then the limit should just be f of a. That's clear. And then if, let's say, I'm going to use a blue now. Right. If when we are plugging in a in f, so I get f of a, you get a 0 over 0. Right. There are actually 4 methods to actually do this. 1, 2, 3, 4. Right. We said that the first method that you actually use, you can always factorize. So you factorize and cancel out the common factor. That's what we said. And then if you can't factorize, but you can see that there is a part that needs to be cancelled. There is either you have a root in most cases. The second thing that you need to do, you need to rationalize. You rationalize the numerator or denominator. So what are you actually rationalizing? Remember, here you're factorizing the numerator and then you factorize the denominator and you cancel the common factor between the numerator and the denominator. Here, in most cases, you'll find out that you can't cancel out the common factor, but you can see that in the denominator there is a part that can be cancelled out. If once you cancel that in the denominator, the function that will remain will be continuous at that point equal to a. So you end up rationalizing the numerator so that we can cancel what is in the denominator. Or if you find out that the numerator, once you rationalize the denominator, is going to make your calculations easy, you rationalize the denominator. So it's only the given equation that will tell you what to rationalize or what to either if you're gonna rationalize the numerator or the denominator. And then if this one is not working and that one is not working, all you need to try is actually the squeeze theorem. So you try the squeeze theorem. You either factorize. If you can't factorize, you try rationalization of either the numerator or denominator. If that cannot happen, you are left with the squeeze theorem. Now we have done all these three, this and that, but once you have actually studied L'Hopital's rule, once you have studied L'Hopital's rule, this is actually the way to go. You usually gonna start with L'Hopital's rule, because if this one can actually be done, L'Hopital's rule can solve it. If this one can actually be done, L'Hopital's rule can solve it. In other words, you always gonna end up starting with L'Hopital's rule, and then after L'Hopital's rule, if it's not working, you can actually try the squeeze theorem. But I highly doubt that L'Hopital's rule is not going to work if these three can work. As long as you have 0 over 0, try L'Hopital's rule. Right. I know that we haven't yet studied this one, L'Hopital's rule. We'll study it after studying the derivatives, but that's how you end up solving limits. L'Hopital's rule is simply saying that the limit as x approaches a, if let's say when you're plugging a, you are getting a 0 over 0. If you are not getting a 0 over 0, you can't use L'Hopital's rule. You only use L'Hopital's rule under the case of 0 over 0. Of f of x divided by g of x. This is the same as the limit as x approaches a of the derivative of f of x with respect to x divided by the derivative of g of x. Right. Take the derivative of this with respect to x and you divide by the derivative of this with respect to x, and then you take the limit. This should actually solve the problem, or it should cancel out the part that needed to be cancelled in the first place. And then if let's say when you are taking f of a, you are getting a number that is not equal to 0 in the numerator, and in the denominator you are getting a 0. We said that there is only one way to solve this. The way to solve this, you just say, I am going to draw a Cartesian plane. So you first gonna draw your Cartesian plane. This is going to be y axis, this is going to be x axis. And then the second thing here that you actually do, you draw a vertical dotted lines at x is equal to a. So if our a is here, so you draw vertical dotted lines at a. And then the next thing that you do here, you pick a value from either side of A, but this value must be very close to A. X is equal to A, right? And so you pick a value here, and then pick another value here, and then after picking those value, right, you plug this value, plug X is equal to blah 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 in F to get the output, right? So you plug that value here. If F of A plus, let's say the value on the right, I'm saying A plus is just saying the value on the right is equal to some positive value, it means that you are going this way. So you draw something like this as you're getting closer to A. If you are getting A minus is also positive, which means that you are going this way on this particular point here. So in this particular case here, you will know that the limit as x approaches A of f of x is equal to positive infinity. But if when you are picking a value here, you get a negative value here, right? If let's say f of A on the right, when I'm plugging it, picking a value on the right, I get a negative value. And when I'm picking a value on the left, I get a negative value, which means now in this function, all you need to draw, you end up drawing, this is saying that on this side we are going that way, on this side we are going that way. And then of course, our limit here is going to be x approaches A of f of x is going to be equal to negative infinity. But if it happens that when you are plugging in, take a value on the left and you're plugging in f, you get a positive value, on the right you get a negative value, then the limit does not exist. If one of these is negative and the other is positive, then we know that the limit does not exist when you're getting a number over 0. That's actually what we actually said. And then if let's say now none of these things are actually working, right? Suppose now none of these things above are not working. What do I actually mean by this? Let me just say none of the above scenarios. This is supposed to be E. Scenarios. If none of the above scenarios happens, so it's either when you are plugging in, you are not getting a number over 0, or you are not getting a 0 over 0, or f is actually, suppose that this one, f is not continuous at that point, fine, and when you are plugging in, you are not getting a 0 over 0, and also you are not getting a number over 0. Then what you need to do, that's when you actually try 9 rules for limits. You remember the 9 rules for limits, that the limit of the addition of two functions is just the limit of each of those. You add them, all those limits, and also the product and the division, all the 9 rules. That's when you try them. And if these 9 rules are also not working or you can't use them, the only other choice that you have now is to try the squeeze theorem. So you try all these things. Remember, the squeeze theorem must be the last thing you try because it's hard to actually find those functions. So the squeeze theorem is the last thing to try, except when you're dealing with those easy functions, whereby we're dealing with trig functions and those that we're forced to find. That's when we used the squeeze theorem, but it must be the last thing that you try when everything else is not working. Now, there are other methods that we use when solving limits. Another one is actually, we usually call it, we can use integration to solve some limits. You can find another function that is actually approximating the given function, and you know that the function that you are using to approximate, you know its limit, or it's easy to find its limit. That's when you actually use other techniques. The one that is actually using integration, I think as the course progresses, we will actually give you an example of how to use integration to solve some of the unsolvable limits when it's actually coming to solving these particular limits. Of course, those questions are way too advanced. I also believe that those actually belong to to students who are doing pure mathematics. For you, I will just be showing you, but they are not really examinable, because you guys, you are only using things that you really need to know to progress. So in your course, maths, you need maths to solve some of the easy problems that only need mathematics background. And also, secondly, the reason you are doing maths is because we want you to improve your logic, so that some of the simplest things, even if you were not taught, but you can try and apply that logic to solve some of the problems that you will be dealing with. Either those of you that are doing commerce, or those of you that will be doing science in general, you find out that some of the things you're just going to be using your logic combined with mathematics background. And of course, I think we'll actually end here, because I think we have done much of this summary is actually more productive and more conducive. It's actually I think it's actually more important that you actually went through this summary and you actually bridged in some of the gaps that you actually encountered. Try and practice and see what you can actually get. And again, since most of you are doing pharmacy and general science, when it comes to this, we usually use it, we don't prove it, and we don't usually use it and ask it in particular. What is Bolzano's theorem saying, or intermediate value theorem? It comes indirectly, as we have seen in factorization and finding the roots of functions. So that's where we say that usually these ones, for those particular reasons, you are not examined on those. Most important thing is continuity and limits. And also when it comes to the precise definition of a limit, you are actually not examined on that. It's only pure mathematicians that are examined on that. Now, the next lesson that we will actually go through here is this. I want you to get familiar with the limit as x approaches either a plus or a negative infinity of f of x. Now, you will notice that what is important here, we have talked about what is happening around a vertical asymptote and what is happening around a whole, in other words, an undefined in a function. And now we want to analyze, remember the main goal of this course, we want you to end up being able to analyze the whole curve, or if you are given a curve, can you give us more information on that curve? Or if you are given a function, can you give us all the important points that we can talk about in that particular function? Now, the only thing we did not talk about is what will happen if we keep increasing x to go all the way to big positive numbers or to big negative numbers. What will be the behavior of the function as we are going increasing the x, right? So that we can actually say that, okay, I can analyze this function around these points, but I know the behavior of that function as we are going to positive infinity or negative infinity. And also you can also now start to characterize what are the horizontal asymptotes, or how to find a horizontal asymptote. So that's one of the important points that I want you to know. Hopefully you got some clarity on this and you actually understood what we were actually doing here. Thank you very much. And also for studying these things they become long, Why they are long? We don't want to make this so short that you end up not getting it at all. There are some parts that you did not really get here, but you still need to practice so that you can understand. But if I were to make this so short, you will end up not getting even more than you are not getting now.